Lecture 2.2, Thermal-Mechanical Interactions. Working is a form of energy transfer. A piston contains an ideal gas that either expands or compresses. From the first law, we know here is that work and energy are the catalysts for change in internal energy. But what we're going to do here is that we're not going to talk at all about heating. Our whole goal is that we want to focus only on working. So then we have to ask the important question: how does K micro change when thermal work is done? And note, I specifically said thermal work. And the reason why is that there are two types of work that we have to consider: mechanical work and thermal work. So before we get to thermal work, let's do a review of mechanical work. So if I look at a review of mechanical work, note that what we're really talking about is what do we mean by positive work and what do we mean by negative work. So let's break it down. So if I have positive work, and again, we're talking about mechanical work, the kind that you learned in your introductory mechanics course. So when positive work is done on a block, it speeds up. So the definition here is that the first thing that we got to do here is that we got to set up our block system. So here's our block. And remember, kinetic energy by itself is meaningless. We have to talk about a change. So then we're going to change the kinetic energy of this block here. So what that means here is that we're assuming that this block starts off with some initial speed, and then work is done, so now it moves at a higher speed. But because energy is a system type of thing, we have to define our system, and our system now is the block. So now, why did the block speed up? So just to make sure, this is our system. The reason why the block sped up here is that there was work done. In other words, there's a force. That force then is applied over some distance. The fact that the force and the displacement are in the same direction, then I have positive work done. So then the work energy theorem then says that there's external work done on the system. And in this case, that work is positive because we said that the displacement and the force were in the same direction. Therefore, the kinetic energy of this block is positive. Now, the way to interpret this thing graphically is that we rewrite this like we've been writing before and said that, yep, here's the kinetic energy. Here's our external force, and it increases the kinetic energy because the work is positive. Now, if I draw an energy bar diagram, what we see here is that the system started with this amount of kinetic energy, which I'm going to call K1. And then all we know here is that the kinetic energy at the end has increased by some value to K2. So this is where I was, and this is where I'm at now. So the only way this could be true here is that there is positive work done. And this is the external work done on the system. And you can clearly see that it's the work that so what we could say here is that we could say here that the work does not disappear, but reappears as kinetic energy in this case, as stored work is the change in the kinetic energy here. So clearly, from our bar diagram, positive work entered the system. That's what we mean by the work energy theorem to change the speed of a block. In a very analogous way, we could say the same thing about negative work. So if I look at negative work, what am I seeing here? Well, when negative work, work is done, the block slows down. So what do I mean by this? Well, I'm going to take my picture here and I'm going to modify it so that I can include it down here for negative work. So if I look at the system, the big difference between the system is that, well, the speeds are different. It starts off at a higher speed, and then it goes to a lower speed. That's what we mean by it being slowed down here. But now what happens here is that the force is not in the same direction as the displacement. The force is in the opposite direction. So then if I look at the dot product, we then say that the work energy theorem, what it shows here is that when I look at that dot product, I'm going to get a minus sign because the force and the displacement are in opposite directions. So when I look at this thing, since this is equal to the change in kinetic energy, this is negative. So picture-wise, how do we see it? Well, I see that I have K1 minus the external work which then reduces the kinetic energy. And again, it's this minus sign that's important. So if I now draw a bar diagram, it visualizes this thing, right? So what I'm seeing here is that the block comes in and it has a high kinetic energy. We know that the block has slowed down because that's how we defined what we meant in this example here. So the only reason why this block slowed down here is that there was work done to transfer energy out of the system. So in this case, we say here is that negative work removes energy from the system. So that's our review of what we mean by positive and negative work. But what does this look like mathematically? Mathematically, mechanical work is an integral, a line integral, as I go from x1 to x2 of f dx here. And we know that this is, of course, the area. So when I look at this, what we really mean here is that, so when we say the area, we really mean that I plot force versus position. And then let's say that this is x1 and then I have x2. I could have just an arbitrary function here. Maybe my work here looks something like this. So then when I look at the area under the curve, this is what we mean by the work here. That area is the work. But this form is not useful. So what we do here is that we rewrite the work function in terms of pressure and volume, because we're dealing with the piston system. We're dealing with pressures, not forces. So this immediately tells us that from the definition of pressure, I can rewrite the force to read pressure times the area. Now, if I go in and I solve this thing, excuse me, if I go in and I substitute this in, then the mechanical work is then going to be, again, the exact same force times displacement. But now I can convert this because now this is pressure, and then area times dx. Well, that's really just the volume. And so if I now redefine, if I now write out what it reads V1, V2 of P dV. And that's what we mean by mechanical work of a piston head. So picture-wise, what does this mean here? So picture-wise, if the volume expands, it's the piston head that moves upwards. So in this case, if delta V is positive, then that tells me that the mechanical work, in this case, which is P dV, that has to be a positive quantity. So if I draw my piston, what do I mean by this? Well, here's my piston. And what I'm imagining here is that I have a piston head right here. And then here is my enclosed gas. So when I look at this piston head, it has moved from 0 this x1 distance. So then I could immediately relate this to the volume because it has to be the area of the piston head. Now, if this thing moves up to, let's say, this height right here, we're seeing here is that the piston has expanded, which then tells us that the volume is then going to be bigger because x2 is larger, which then implies here that V2 is equal to V1. Now, I think this is a really key point in talking about what is the difference between mechanical work and thermal work. So the key point to remember is this. This expansion never mentions anything about the gas itself. This viewpoint is about the state of the piston head, not the gas. This is the standard definition of work. But it's not a good definition for thermodynamics. In thermo, our goal is to describe the behavior of the gas, not the piston head. Therefore, work has to be redefined. And then this way, we interpret the increase and decrease in microkinetic energy. So here we go. We're going to redefine work as thermal work. Or maybe I should say mechanical work as thermal work. Thermal work tell us how K micro increases and decreases before and after gas gases collide with the piston head. This requires the addition of a minus sign. And it makes sense. And the reason why, because if you look at Newton's third law, we know that if we have a force that acts on one, if one acts on two, then there's going to be an equal and opposite force between 2 and 1. That minus sign is derived from Newton's third law. So then if we then go in and we define it as thermal work, from now on, I'm going to call it work because we're only interested in thermal work. Newton's third law says, yep, there's that minus sign. Instead of the piston, we now look at the gas collisions. And that's the only change. But it makes a huge, huge difference. By interpreting it this way, we can then have sort of like an overview of what happens. So if we compress a piston, what does that do? Of course, that decreases volume. But now what you're finding here is that if I focus on the gas, this is positive work by the piston on the gas, which then increases the microkinetic energy to be positive. On the other hand, if it expands, if you expand a piston, then you increase volume. But what you're going to find here is that the only way a volume can increase is if there's collisions by the gas particles. In other words, the gas particles lose kinetic energy, and that turns into the work on the piston, which then gives you a decrease in kinetic energy. So let's write this out. So if I have a decreasing volume, which is a compression, so a decreasing volume increases K micro. So let's go through a series of steps for you to see that. So the first thing is, let's draw a piston. Let's say that here's my piston. And what I'm going to do here is that I'm going to compress the piston. So in other words, it's going to be moving down. So as I compress it, it starts off with some volume of V1. And then if I compress it, let's say I get to right here, you're going to see here that, of course, that volume is then going to be smaller. So I'm compressing the gas in this situation. So here goes my series of steps. I have a decrease in volume. That in turn means that V1 is greater than V2, and therefore the change in volume is negative. Not a surprise. But now, if I focus on thermal work, I now have positive thermal work. Now, why is thermal work positive? Well, it turns out that I have two minus signs. There's the first definition, the first minus sign from the thermal, how we went to thermal, from mechanical work to thermal work. But then the integral of PdV, since delta V is less than 0, I get a minus and a minus. And as a consequence, I get a positive quantity. In other words, I have two minus signs, right? I have two minus signs. That's why that's a positive quantity. So then if I go in and I look at this here, so now if I have positive work, we know that positive work increases K micro. The gas particles go faster. So as a consequence, that plus sign, according to the work energy theorem, or the first law, then has a positive change in internal energy, which therefore K micro is then going to also be positive. This is the intuition, right? This is your intuition, not the other way. And to see why this is your intuition is that take a systems viewpoint. And if I take a systems viewpoint, what I see here is that I have a gas. And what am I going to do? That gas is going to have work done on it. From what we just said, we start off with a low kinetic energy or a low initial speed, and then this increases in kinetic energy. So V2 must be larger than that. So why is this intuitive? Because if I add or do work on the system that's positive, it increases the available energy. So in this case, we know that we're going from little k1 to big K2. The only way you can do this is if you add work. And here's my process. I am doing work to increase the energy of that system. Now, from a bar diagram viewpoint, it's real obvious, because now what we see here is that this guy starts off with this amount of kinetic energy, and then it increases to K2, right? We know that. So the only way this could be true here is if I do work. That work is positive work, and that's what increased the kinetic energy here. As a point of reference, if you stuck to mechanical work, note there's no extra minus sign. So where would the mechanical work be? It would be negative here. How can I envision this negative mechanical work increasing kinetic energy? It's because you have to redefine work to look at this thing. That's why we don't do that. So now let's go look at this thing physically. So this is going to be a physical explanation here. So what do I mean by a physical explanation? That means we have to explain why does K micro increase. So the way you want to do this here is that you want to visualize a moving piston head that collides with a gas particle. And the best analogy that I can think of, which is one that should be common to all of you, is a bowling ball, a golf ball collision. And we'll assume that this collision is elastic. So let's look at this thing here. So if I look at this thing, here's my before, and then I'm going to have my after. And so what I'm going to have here is that I'm going to have this situation. I'm going to have a bowling ball, right? Here's my bowling ball. And what I'm going to see here is that I have a golf ball. So in this situation, I have a bowling ball. And then over here, I have a golf ball. Now, what you're going to see here is that I'm going to copy these for to use again here. And what you're seeing here is that the bowling ball is coming in like this. And I see that I have a slow moving golf ball. Now, it could be fast, but if you remember elastic collisions, the fact that the mass of the bowling ball is much larger than the mass of the golf ball, after the collision, the speed of the golf ball is about 2 times the speed that when it came in. In other words, if I look at the scenario here, I have this. I have this situation where now I'm seeing here that the golf ball afterwards has a much higher speed. It's clearly faster. So using conservation of momentum, or I could have used conservation, the work energy term, but I think conservation of momentum is a little bit cleaner, shows the golf ball has a higher speed after the collision. So that means that K micro increased, right? That means that it increased, of course. But what, so if I now look at this thing, we then see here that K2 is greater than K1. Now let's apply this to the piston gas collision. So now I want to apply this to the piston head gas collision. The situation is identical. So why is it identical? Because if I look at beforehand and I look at it afterwards, well, the piston head is way more massive than the golf ball. Than the gas particle. It's like enormously bigger. So if I see the piston head coming down, after the collision, it's going to continue to move down. So what do I see here? I see that the golf ball is going to be coming in and then it's going to be leaving. But the way it comes in here is that its speed before and after has increased dramatically. So what we say here in the language of what we're talking about, the gas particle moves faster after the collision due to the work of the piston head. And so when I look at this, I now have positive work of the piston head. Why? Because its displacement is in the same direction of the force that it's going to apply. So this automatically makes it positive. So therefore, the change in microkinetic energy is also positive. In other words, it increases K micro as expected. On the other hand, we have the situation where we have increasing volume. In other words, in expansion, increasing volume decreases K micro. So again, we want to go through the steps. So let's start here. So what I'm seeing here is that here's my piston head. So if I look at my piston head, if I have an increasing volume, that means that the volume is moving upwards like that, or the piston head is moving upwards. And again, I now have my trapped gas right there. So I can see here is that this starts off at some volume V1, and then it's going to expand so that it reaches a larger volume, which we'll call V2. So now let's go look at the details of the work to get the signs issues right. So here we have an increase in volume. But if I increase in volume, that tells me that V2 must be bigger than V1, which now tells me I now have a change in volume that's positive. Now, in thermodynamics, we say that this is negative work done. And so the reason why it's negative, because now if I look at my work here, I have a negative sign, but now the pressure times the volume, that is a positive quantity. So I get a minus times a plus, that is less than zero. So again, I have a negative times a positive, which of course is going to give me a negative. That's why it's negative. So now what we say here is negative work decreases K micro. And that makes sense because now think about what's happening now. So let's look at the systems viewpoint. If I look at the system, I have my gas right here. And what I know here is that there's going to be a decrease. So if there's a decrease, that means here is that I start off at some high initial velocity, and then I go to a lower velocity. So why is there a decrease? Because there is energy being removed from the system. It's leaving the system. So what I'm seeing here is that I got a K1 here and I got a small K2. So then what's going to happen here is that means here that my work here must be negative. But that's still work here. So to get a good sense of that, I'm going to use a bar diagram to make this nice and clear. So when I look at a bar diagram, it tells me this. I look at the kinetic energy. It's a high kinetic energy initially, and then I'm going to go to a lower kinetic energy. So the only way I can decrease it is that if I do negative work, which is exactly what we were just talking about. It's this negative work that actually tells us this. Now, just to give a physical explanation of this, here's what we should be thinking about. So I'm going to use the same analogy. So I have my before and I have my after. In fact, I think I still have it in my, yep, there it is. I didn't realize that's a score. And so what I'm going to see here is that I have the same type of situation. So what am I going to do here? Here's what I'm going to see. This time, I'm going to say that the bowling ball is stationary. So as this guy comes in, I'm going to say that this guy has a high velocity. Now, after the collision, the bowling ball moves forward and the golf ball moves in the opposite direction, but at a slower speed. That's conservation of momentum right there. So what we're seeing here is that the golf ball has a slower speed after the collision. So therefore, that has to be a decrease in K micro, or, or just kinetic energy. That's using arguments of momentum. But then I'm just going to apply this same situation. So I'm going to apply this situation to our piston head gas collision. So as before and after, I have a stationary piston head. And then what I'm going to do here is that I'm going to send in a high speed gas particle. So then if I do that, that means I'm going to have a high velocity here. And then after the collision, the piston head moves and the ricochet of the gas particle reduces part of that momentum transfer. So from conservation of momentum, the gas is moving slower after the collision. So then that tells us here is that the work done by the gas decreases K micro. In other words, the work of the gas is negative because the force and the displacement are in two different directions, which then tells you that the change in the microkinetic energy is also negative.